You've probably seen the 3 blue 1 brown video on the hairy ball theorem, but there is an even more elegant proof by Hopf back in 1946, which we are going to illustrate. To catch everyone up to speed, the hairy ball theorem roughly states that a smooth tangent vector field on a sphere will always have some point where it vanishes. In this illustration, there are 2 points, the north and south poles where the vector field vanishes. You can still put tangent vectors on those 2 points, but the resulting vector field is no longer continuous. It doesn't have to vanish at 2 points though. In this picture, there is only 1 point where it vanishes, but there can't be none. That is the statement of the hairy ball theorem. The points where the vector field vanishes are called zeros. And to prove the hairy ball theorem, it seems very natural as a first step to study vector fields with zeros. Let's consider a much simpler setting, a vector field on a flat surface. In this illustration, we have a zero right in the middle, which acts like a source where all vectors point away from. Of course, a zero can also look like a sink, where all vectors point towards. But there are other things a zero can look like. This is known as a saddle, a kind of combination of both a source and a sink. Along the vertical direction, it is attracted towards the middle, but along the horizontal direction, it is repelled away from the middle. It can also look like a magnetic field, which is known as a dipole. In these examples, the zeros look different from each other, but can we be more precise than saying they look different? Well, the answer lies in something called the index. The idea is to encircle the zero and look at how the vector field changes around it, starting from some random point around the zero. The vector field at this location points towards the top right and makes an angle with the positive x direction. Let's call this angle alpha. Now, if we pick some other point, the vector field there points in a different direction and makes a different angle with the positive x direction. We are interested in how this angle alpha changes. As we go around the zero counterclockwise, the angle keeps increasing until it hits a full turn, resets to zero, but then it keeps increasing later. However, if we allow ourselves to go beyond the full turn, then this angle can keep increasing continuously. In that case, alpha has increased by 2 pi. We define the index as the change in this angle divided by 2 pi, which is plus 1 in this case, since alpha has increased by 2 pi. We can repeat the analysis for a sink. First, we pick a random point around the zero, then figure out the vector attached to this point and the angle alpha it makes with the positive x direction. This time, the angle keeps increasing when we go around the zero and has increased by a full turn 2 pi, similar to the previous case. Therefore, the index as defined by change in alpha divided by 2 pi is still plus 1 for a sink. What about a saddle? Again, we pick a point, see the vector at that point, and measure the angle made with the positive x direction. This time, the angle keeps decreasing instead and can keep decreasing continuously if we allow it to go to negative values, in which case alpha has decreased by 2 pi, and so the index for a saddle is minus 1 instead, since the angle decreases. What about a dipole? Again, we pick a point, see the vector at that point, and measure the angle made with the positive x direction. This time, the angle increases very quickly and makes 2 full turns when we go around the zero. So for the dipole, alpha has increased by 4 pi, and the index, being the change divided by 2 pi, is plus 2. In general, we can classify different kinds of zeros by their indices, and we saw that the indices of sources, sinks, saddles, and dipoles are plus 1, minus 1, and minus 2 respectively. Now we extend this discussion to vector fields on surfaces. For example, this vector field has a zero which looks like a source, and we expect the source to have index plus 1. The intuition is correct, but when we try to properly define an index on a surface, unlike on a flat plane, there isn't the equivalent of positive x direction that is also tangent to the surface. So we construct a tangent vector field to make that the positive x direction, which serves as a reference direction, from which we can determine the angle alpha made with the vector attached there. Then we can go around the zero and look at the change in this angle like before. In this case, this angle has increased by 2 pi, which means that the index, still defined as the change in the angle alpha divided by 2 pi, is plus 1 as expected for a source. Let's go beyond a single point, zoom out and look at the whole vector field on the sphere. In addition to the source on top of the sphere, there is also a sink at the bottom where all vectors point towards. Both the source and the sink have index plus 1, so the sum of indices for this vector field is plus 2. But if you look at some other vector fields on a sphere, like this one, which is a dipole, the index is plus 2. Since there are no other zeros in this vector field, the index sum is also plus 2. Hang on a minute, both these vector fields have index sum plus 2. Is it always the case? If we can prove this is always plus 2, then because a vector field with no zeros should have an index sum of 0, we would reach a contradiction. Then vector fields can't have no zeros on the sphere, which is the Hairy-Ball theorem. So now we only need to focus on showing why the index sum is always plus 2. The strategy is that given any two vector fields f and g, and their index sums if and ig, we prove that the difference if minus ig equals 0. To do that, let's zoom back into some zeros and compare the indices of the two vector fields. At a particular point around the zero, there are 3 different vectors of interest. First, the reference direction, and the 2 vectors from the vector fields f and g at this point. To determine the indices of the zero from the 2 vector fields, we measure the angle between f and the reference direction, as well as that between g and the reference direction. The index from vector field f minus that from g is the change in alpha f minus alpha g when you go around the zero divided by 2 pi. The difference alpha f minus alpha g is the angle between the 2 vector fields, and we don't need the reference direction at all. Hence, the difference in the index contributions from f and g is the change in the angle between them as we go around the zero. In fact, this works even without going around a zero. The the indices are 0 and the net angle change is 0, so the formula still works. It also works if it is a 0 of f but not g, or a 0 of g but not f. As long as the path encircles at most 1, 0, this formula works. Given the positions of the zeros of f and g, we subdivide the sphere into sufficiently small regions so that each region contains at most 1, 0. Then, we can use the formula that we derived in each of them. As we sum over the regions, the first term will add up to the index sum of f, and similarly, the second one adds up to that of g. For the change in the angle between f and g, we focus on this edge between the two regions. The angle change is always measured counterclockwise, so for the region to the right of this edge, it is traversed from top to bottom. But for the region to the left of this edge, it is instead traversed from bottom to top, which cancels out. This is true for all edges, so the total change in this angle is 0. This is exactly what we wanted. The index sum of any two vector fields on a sphere is the same. Since there is a vector field on a sphere with index sum plus 2, all vector fields on a sphere must also have index sum plus 2. A vector field with no 0 has a vanishing index sum, and that is not possible. Ta-da! But things don't end here. After all, the way that we define an index extends to all surfaces. Even the argument that two vector fields have the same index sum doesn't depend on the surface being a sphere. So if we're on, let's say, the torus, any two vector fields also have the same index sum. It's just that this time, the index sum on the torus is 0. You can play the same game for other surfaces too, and you might notice a pattern. The index sum is actually the Euler characteristic of the surface. This is known as the Poincaré-Hopf theorem, and it's the same Hopf that gave the previous proof. In fact, he was trying to prove the more general theorem rather than just the hairy ball theorem. Here's a quick reminder of what Euler characteristic is. First, divide the surface into triangles, and then compute this quantity v minus e plus f, where v denotes the number of vertices in the triangulation, e denotes the number of edges, and f denotes the number of faces or regions. It turns out that v minus e plus f is the same for any triangulation on a given surface S called the Euler characteristic of the surface, denoted as chi of S. We're about to kill two birds with one stone. We'll see why this number doesn't depend on how you triangulate the surface, and at the same time, prove the Poincaré-Hopf theorem. It's basically just one diagram given in the book Hopf authored. The idea is that with your favorite triangulation of the surface, we construct a vector field where each triangle looks like this. The vertices act like sources where vectors emanate from. The midpoint of the edges act like saddles, with an attracting direction and a repelling direction. And the interior of this triangle acts like a sink. Now consider the index sum that comes from such a vector field. Each source has index plus 1, and since all vertices act like sources, they contribute v to the index sum. Similarly, since each saddle contributes index -1, and each edge contains a saddle in this vector field, they contribute -e to the index sum. Finally, each triangle interior acts like a sink, which has index +1, and so they contribute f to the index sum. Overall, the index sum is exactly the Euler characteristic. Since we have proved that for a given surface, the index sum is fixed, we've now also shown that any triangulation must have the same value of v minus e plus f, and of course, the Poincaré-Hopf theorem, where the index sum is the Euler characteristic. We started with the Hairy-Ball theorem, where the index sum not zero implies the impossibility of a nowhere vanishing vector field, but we end up with the more general Poincaré-Hopf theorem without much more effort. If you enjoyed this video, subscribe and consider supporting on Patreon, and I will see you next time. Bye!